You hear about cutting-edge technology, lasers, plasma cutters, water jets that slice through titanium. But there's something older, simpler. A handheld tool that burns at 4,000 degrees Fahrenheit and cuts through 3/4-inch hardened steel in 2 seconds. No electricity needed, no heavy tanks, just rust and aluminum powder reacting the way they did in 1893. The thermite torch. Military calls it a game changer. Rescue teams call it a lifesaver. Engineers call it impossible until they see it work. How does a chemical reaction discovered in a German laboratory cut through what's supposed to be impenetrable? Why did it take over a century to make it handheld? And what happens when you put that kind of heat in someone's palm? He's 28 years old, working in his father's chemical factory, trying to purify chromium and manganese without carbon contamination. Standard smelting uses coke, leaves traces. Goldschmidt wants pure metal, so he mixes aluminum powder with iron oxide. Rust, common rust. Then he ignites it. The mixture doesn't explode, it does something else. The aluminum rips oxygen atoms straight out of the iron oxide molecules. The reaction generates 2,500 degrees Celsius, 4,532 Fahrenheit. Molten iron pours out, pure iron. The aluminum becomes aluminum oxide slag, no carbon anywhere. The heat alone could weld train tracks. Goldschmidt realizes this immediately. March 13th, 1895, German imperial patent, number 96, 1317, the thermite process. The Goldschmidt reaction, it changes everything. No bolts, just metallurgical bonding at 2,500 degrees. The weld holds. 1900, Goldschmidt establishes Allgemeine Thermit-Gesellschaft. The thermite company goes global. 1909, Tokyo tram rails. 1911, Switzerland's Seetalbahn Railway welds 1,000 meters of continuous track. Those welds still show no wear in 1924. 13 years without degradation. By 1928, the Deutsche Reichsbahn approves thermite as the standard railroad welding process. Continuous welded rail becomes possible. Less vibration, longer rail life, better ride quality, reduced maintenance. But that's just welding. The cutting application? That's coming. Not thermite powder in a mold, metal tubes, 2 concentric pipes. The space between them filled with flux, sodium carbonate, borax, sodium chloride in equal proportions. Oxygen flows through the inner tube. When you heat the iron tube to 900 degrees Celsius and add pure oxygen at 4 to 10 bar pressure, the iron itself becomes fuel. 4 iron plus 3 oxygen yields 2 iron oxide plus massive heat. The tube burns, consumes itself. Temperatures hit 3,500 to 4,500 Celsius, hot enough to cut through steel, concrete, rock. The lance operator feeds oxygen, watches the tube melt forward like a flaming spear, cutting through materials that would stop conventional torches. Every few minutes, the tube burns down to a stub, operator shuts off oxygen, discards the remaining piece, starts a new lance, industrial demolition. Furnace maintenance, cutting seized axles from cranes and ships without damaging the bearings. The thermal lance spreads through foundries and scrapyards worldwide. Documentation dating to March 1895, verified through German imperial patent records, cross-referenced with technical papers from the Journal of Materials Science published in 1993, examining aluminothermic reaction synthesis, and confirmed through industrial application data from the American Railway, Engineering and Maintenance of Way Association's 2,000 technical reports on thermite rail welding spanning. From 1899 to present-day continuous track installations. Now back to the information. Impact drives a needle into a percussion cap, ignites the thermite filling. Then the magnesium casing itself ignites at 650 Celsius, sustains combustion at 1,100 degrees, releases vapor that burns at 1,800 Celsius, hot enough to melt through steel roofing and girders. Wooden cities burn completely. The 4-pound incendiary bomb developed by ICI becomes the British standard. Hollow aluminum magnesium alloy body with cast iron nose filled with thermite pellets. Burns for 10 minutes. RAF Bomber Command produces 35.8 million of them in 1944 alone. Cities like Dresden and Tokyo burn for days. March 9th to 10th, 1945. Tokyo firebombing. 25% of the city's buildings destroyed. 80,000 dead. 1 million homeless. The thermite doesn't care what it burns. It just needs oxygen and fuel and ignition temperature. Military also uses thermite grenades, anti-material roll, emergency destruction of equipment. You drop a thermite grenade into a howitzer breech and close it. The grenade burns, welds the breech shut, guns permanently disabled, no explosion, no noise, perfect for covert sabotage. Cryptographic equipment threatened by enemy capture, thermite charge. 2 minutes later, there's molten slag where classified machines used to be. The simplicity becomes the weapon. Not all thermite welds, but the aluminothermic process dominates. Modern charges are refined, different hardness levels to match rail types. 285 Brinell hardness for standard rail, harder formulations for premium track, grain size controlled for better strength and fracture toughness, A single thermite weld completed in under 1 hour with portable equipment. Track workers carry molds, thermite charges, igniters. Align the rail ends with 25 to 30 millimeter gap. Secure them in a refractory mold. Preheat the rail ends to 1000 Celsius with oxyacetylene torches. Prevents thermal shock. A pre-weighed thermite charge sits in a crucible above the mold. Aluminum powder and iron oxide mixed to exact ratios, 2.96 to 1 by weight for standard iron 3 oxide thermite. The charge ignites. The reaction hits 2500 Celsius within seconds. Superheated liquid iron pours into the mold, melts the rail ends, fills the gap, forms homogeneous metallurgical bond, solidifies in 1 to 2 minutes. Workers remove the mold, grind the weld to restore rail profile. The track is seamless, trains run smoother, rail fatigue decreases, maintenance intervals extend, Goldschmidt's descendants. Still producing welding thermite globally through companies like Degussa and the modern Goldschmidt Group. Compact, lightweight, handheld, fast deployment, 2011. United States Air Force Small Business Innovation Research Program. Microscale Ordnance Technology, SBIR. Energetic Materials and Products. Incorporated, EMPI. Dennis Wilson, Principal Investigator. Dr. Stephanie Johnson, Program Manager and Research Chemist. The challenge: miniaturized thermite cutting into a handheld device that special operators can carry on missions. No tanks, no hoses, self-contained, safe to use inches from the operator's hand. The team spends 2 years developing the concept. 2013, they achieve it. The Tech Torch, thermal erosive cutting torch, 12 to 14 inches long, 1.5 inch diameter, less than 1 pound with cartridge loaded, fits in a backpack, one-hand operation. Additives for maximum temperature and velocity. Engineered graphite nozzle, different geometries for different applications, flat blade configuration for cutting rods, round jet for penetrating plates, internal electric igniter. The operator loads the cartridge into an electric handle. Handle supplies, small electrical charge for ignition, redundant safety features, LED arming switch, fire button, 9-volt battery. When the operator activates it, the thermite ignites inside the cartridge. Burns for 2 seconds. The combustion products, vaporized metal and particulate matter, exit through the nozzle at over 4,000 degrees Fahrenheit. The temperature and velocity of the metal vapor jet heat the target above its melting point. The force erodes the material away. Mechanical agitation from the gas jet. Thermal cutting from the intense heat. The cartridge contains all the pressure and thermal energy safely. No backblast. No injury risk within inches of the operator's grip. 2 cartridge designs. Rod cutter. Cuts solid steel rod up to 0.75 inch diameter. Hardened steel. Plain carbon. Stainless. Doesn't matter. 2 seconds. Clean cut, plate penetrator, creates 0.35 inch diameter hole through 0.5 inch steel plate, 2 seconds. The cartridges work in combination. Cut a lock shackle with the rod cutter, burn through the lock body with the plate penetrator, breaching complete in under 10 seconds total. No loud grinding, just the hiss of oxygen and the spray of sparks. Operators love it. Replaces 16-pound cutting torches with oxygen tanks and hoses and ignition systems. Fits in a cargo pocket. Ready in seconds. MPI provides over 600 handheld units to special operations and law enforcement by 2015. Feedback drives design changes, handle length adjusted, safety modifications, reliability improvements. The technology attracts attention beyond military use. Law enforcement, forced entry for hostage rescue, first responders, trapped victims behind steel doors or reinforced structures, explosive ordnance disposal teams, cutting through unexploded ordnance casings, underwater salvage operations. Works underwater because thermite supplies its own oxygen. It doesn't need air. The thermal erosive cutting principle proves versatile. Stephanie Johnson explains the physics. It works through chemistry and physics combined. The extremely high heat renders steel to a molten state. The force of the propulsion erodes the material very rapidly, not just melting. Erosion. The metal vapor carries kinetic energy, impacts the target, displaces molten material as it forms, prevents resolidification, keeps the cut advancing. Temperature matters. 4,000 degrees Fahrenheit, roughly 2,200 Celsius, about twice the melting point of steel. Steel melts at approximately 1,370 Celsius. 4,000 degrees provides thermal margin, ensures complete liquefaction even with heat dissipation into surrounding material. The velocity matters too. High-speed metal vapor jet entrains molten material, carries it away from the cut zone, creates clean kerf, no slag buildup, no clogging. The nozzle geometry controls the jet shape, flat blade, round penetrator, angled cut, straight bore. Each application needs specific thermal flux pattern. EMPI engineers the nozzles using computational fluid dynamics and experimental testing. Graphite withstands the heat, channels the flow, maintains jet coherence across the 2-second burn time. describes it as a thermite-based high-temperature and high-velocity metal vapor jet. Notes the cartridge design contains intense pressure and thermal energy, safely within inches of operator's hand. Highlights the ability to cut 3/4-inch hardened rod in 2 seconds. The article mentions MPI's development timeline. 2011, start under Air Force SBIR. 2013, introduction to special operations. By 2015, the technology enters Phase 3, manufacturability and quality control. Production rate increases from dozens of units per day to target of 1,000 units per day. The scaling requires precision manufacturing. Each cartridge must ignite reliably, burn consistently, produce predictable jet characteristics. Quality control testing involves cutting standardized steel samples, measuring penetration depth, analyzing kerf geometry, verifying ignition reliability across temperature ranges. Military equipment must function in desert heat and Arctic cold. Tech Torch undergoes environmental testing, extreme heat, freezing conditions, humidity, saltwater spray, shock and vibration. The cartridges must survive rough handling and still ignite on demand. The safety testing is extensive. Worst case scenarios. Cartridge dropped from height, exposed to flame, subjected to impact. The internal energetics must not detonate accidentally. The containment must hold. The igniter must only activate with correct electrical signal. Redundant safety features prevent accidental discharge. Sequential cutting for complex breaches. The Tech Torch doesn't replace all breaching tools. Explosives still have roles. Mechanical breaching for certain scenarios. But for situations requiring speed, silence, and compact equipment, the thermite torch proves superior. Field reports come back. Afghanistan, Iraq, Africa, urban environments, rural obstacles. Operators cut through reinforced gates, vehicle barriers, improvised defenses. The 2-second cutting time matters in tactical situations. Speed of action, element of surprise, reduced exposure time. The tool changes breach planning. What used to require minutes of setup and cutting now takes seconds. The psychological impact. Defenders see their steel barriers defeated instantly. Mounted cameras show the torch cutting through locks and hinges faster than they can react. The simplicity of the chemistry, rust and aluminum. Same reaction Hans Goldschmidt discovered in 1893. Scaled down, controlled, directed through engineered nozzles. The temperatures achieved in a Berlin laboratory in the 19th century now deployed from a pocket-sized device in 21st century combat zones. Barricaded suspects, reinforced doors, time-sensitive entries, traditional breaching methods, explosive charges, ballistic breaching, hydraulic spreaders, ram tools. Each has limitations. Explosives create overpressure, risk to hostages, structural damage. Ballistic breaching expends ammunition, may not defeat hardened targets. Hydraulic spreaders require setup time, space to position the tool. Ram tools need multiple strikes, generate noise. Alert suspects. The Tech Torch offers alternative. Quiet operation compared to explosives. No overpressure wave, no fragmentation. Precision cutting. Can target specific components, hinges, locks, reinforcement bars. The thermal effect is localized. Minimal collateral damage to surrounding structure. Training differs from military operators. Law enforcement focuses on building entry. Vehicle extractions, infrastructure access. But the principles remain. Load cartridge, aim at target, activate, 2 seconds, move through. The legal frameworks around thermite torch use vary by jurisdiction. Some classify it as destructive device, requires special licensing. Others permit it under law enforcement exemptions. EMPI navigates these regulations, works with agencies to ensure compliance, provides training and certification programs. Fire departments, search and rescue teams, vehicle extrication scenarios, car accidents with victims trapped. Steel frame vehicles, reinforced pillars. The Tech Torch cuts through A pillars and B pillars faster than hydraulic cutters. Less time to extraction, better patient outcomes, building collapse rescue, victims trapped under steel beams, rebar reinforced concrete. Traditional cutting takes hours, rotary saws, thermal lances with tanks. The handheld thermite torch provides faster access. Cut through obstructions directly above victim locations, create extraction pathways. The underwater capability matters. Submerged vehicles, water rescue. The thermite reaction doesn't need atmospheric oxygen. Works in water, marine salvage operations, cutting through ship hulls, underwater infrastructure repair, offshore oil platform maintenance. The tool finds applications beyond emergency response. Industrial maintenance, steel mills, furnace repairs, slag removal, cutting through solidified metal buildup. Traditional methods require cool down periods, mechanical cutting, thermite lancing. The Tech Torch offers portable alternative, rapid cutting without extensive setup. Demolition industry, controlled structure dismantling, cutting through steel beams, reinforced concrete. The precision matters. Selective cutting. Avoid destabilizing entire structures. The 2-second burn time allows for multiple cuts in sequence. Methodical dismantling. But provide ignition energy. Magnesium strip, sparkler, temperature above 1000 degrees. The reaction initiates, becomes self-sustaining. The aluminum has higher affinity for oxygen than iron does. Thermodynamics drives the reaction. Aluminum steals oxygen atoms from iron oxide, forms aluminum oxide, releases pure iron. The energy released, 945.4 calories per gram, 3,956 joules per gram. Energy density, 16,516 joules per cubic centimeter for pressed thermite. The temperatures achieved. Adiabatic burn temperature, 3,135 Kelvin, 2,862 Celsius, 5,183 Fahrenheit. The iron itself boils at 3,135 Kelvin. 78.4 grams of iron vapor produced per kilogram of thermite. The molten iron, the aluminum oxide slag, the intense heat, all from simple oxidation reduction chemistry. The reaction products contain no gaseous emissions, almost no gas production during burning. Unlike explosions, unlike combustion of organic fuels, thermite burns without expanding gases, pressure buildup. The reaction is self-contained, dense, focused. Perfect for cutting applications where you need heat without blast effects. Refractory materials for the casing, heat-resistant composites, or the internal arrangement. Thermite mixture optimized for velocity and temperature. Binders to press the mixture into stable form. The graphite nozzle, precisely engineered throat geometry. Expansion ratio, exit angle, the igniter, small pyrotechnic charge, responds to electrical current, generates sufficient heat to initiate thermite reaction. The igniter must function instantly. No delay, predictable activation. The electrical interface, coaxial connector, 1 inch diameter by 1 inch long, forms mechanical joint and electrical connection simultaneously. Standard connector used across all cartridges. Allows for splitter cables and extension cables. Modular system. Operators assemble custom configurations for specific missions. The safety interlock, multiple fail-safes. Handle must be armed. LED indicator confirms arming status. Fire button must be deliberately pressed. Prevents accidental activation. The handle design. Ergonomic grip. Balance point optimized for one-hand operation. Control surfaces easily accessed without shifting grip. The electrical system. Battery compartment. Simple 9-volt. Available worldwide. Circuit protection. Prevents over-discharge. Ensures reliable power delivery to igniter. Thermite mixture prepared under controlled conditions. Purity of components critical. Aluminum particle size. Iron oxide crystal structure. Ratios measured precisely. Deviations affect burn rate and temperature. The mixing process. Blending equipment. Prevents contamination. Avoids premature reaction. Static discharge risks. The pressing operation. Hydraulic presses. Create dense thermite pellets. Higher density. Slower burn speed. More controlled reaction. Better penetration power. The cartridge assembly. Automated production lines for consistency. Each unit tested. Igniter continuity checked. Structural integrity verified. The quality assurance. Statistical sampling. Performance testing. Cut standardized steel specimens. Measure cutting time. Analyze kerf characteristics. Thermal imaging during burn. Verify jet temperature and velocity. The batch tracking. Traceability from raw materials through finished product. Lot numbers. Manufacturing dates. Performance data archived. Military requirements demand this documentation. Liability concerns. Regulatory compliance. Robotic deployment. Small unmanned systems. Drones equipped with cutting capability. Remote operations. Hazardous environments. The oil and gas industry interest. Wellbore operations. Stuck pipe cutting. Downhole equipment removal. The extreme conditions. High pressure. High temperature. Corrosive environments. Traditional cutting methods struggle. Thermite-based cutting provides alternative. Chemical stability. No moving parts. Simple activation. The commercial market potential. Construction industry. Steel fabrication shops. Salvage yards. But regulatory hurdles remain. Civilian access to thermite devices. ATF licensing requirements. State and local regulations. The liability questions. Tool misuse. Accidental injuries. Property damage. EMPI focuses on professional markets. Military. Law enforcement. Licensed industrial users. The technology proves viable. The applications expand. But widespread civilian availability, unlikely near term, or vaporizes directly. Solid to gas phase transition. The heat sources vary. Oxyacetylene torches, combustion of acetylene and oxygen, peak temperature 3,100 Celsius, plasma arc cutting, electrical arc ionizes gas, creates plasma jet, temperatures exceed 20,000 Celsius, laser cutting, concentrated light energy, heats small spot to vaporization, thermite cutting, exothermic chemical reaction, produces molten metal and superheated vapor. Each method has characteristics: speed, precision, heat-affected zone, material compatibility, equipment complexity, cost per cut, thermite cutting advantages, no external power required, self-contained reaction, works in any environment, including underwater, Vacuum conditions, disadvantages, single-use consumable, 2-second burn time limits, cut length. Heat-affected zone, relatively large compared to laser, but for portable breaching applications. The advantages outweigh limitations. Speed of deployment, reliability, simplicity. 1899, first commercial application. Tram-track welding in Essen, early 1900s. Thermite welding spreads globally. Railroad industry adopts continuous welded rail. 1922, Leo Malker develops thermal lance. Metal tube filled with flux, burns an oxygen stream, cuts through steel and concrete. 1930s, World War II development. Thermite incendiary bombs. Allied and German forces employ them. City-destroying firebombs. Post-war. Thermite welding dominates railroad construction and repair. Thermal lances become industrial standard for heavy cutting. 2011. MPI begins miniaturization research. U.S. Air Force funding. 2013. TT torch introduced. Handheld thermite cutting device. 2015. Military and law enforcement adoption. Over 600 units deployed. Present day. Technology continues evolving. New applications emerging. The same fundamental chemistry. Aluminum reduces iron oxide. Temperature remains 2,500 Celsius, but the delivery mechanism transformed from laboratory curiosity to industrial process to military tool to handheld device. 130 years of development. The chemistry unchanged, the engineering refined. Other companies develop similar technologies, thermal cutting systems, exothermic breaching tools, but the tech torch remains notable. First successful miniaturization, proven field performance, military adoption. The patents protect core technologies, nozzle designs, cartridge construction, ignition systems. EMPI maintains technological lead, continued research investment, customer feedback integration. The market size remains limited. Professional users only, military procurement, law enforcement agencies, industrial contractors, not consumer product. The unit costs, classified for military sales, estimated hundreds of dollars per handle. Cartridges, consumable, cost per use. Compared to alternatives, explosive breaching charges, plasma cutter systems, hydraulic tools. The thermite torch occupies specific niche, situations requiring portability and speed, where setup time cannot be tolerated, where environmental conditions preclude other methods. The return on investment, lives saved through faster rescue, missions accomplished through rapid breaching, equipment disabled through covert action. The calculus justifies the cost for the organizations that need it. The technology proves invaluable. But effective employment requires skill, target assessment, material identification, structural analysis, where to cut for maximum effect, how to sequence multiple cuts, safety considerations, clearing personnel from spark spray radius, ensuring stable platform for operator, the tactical integration, breaching teams coordinate roles. One operator handles tech torch, others provide security, communications, medical support. The timing matters. Breach initiation synchronized with entry team movement. Minimize time between breach and entry. Reduces defender reaction window. The contingency planning. What if cartridge fails to ignite? Backup breaching method ready. What if cut incomplete? Second cartridge prepared. What if defenders reinforce breach point during operation? Alternative entry points identified. Military doctrine incorporates thermite torch capabilities. Update its tactical manuals. Includes tool in standard equipment lists. Training courses establish operator qualification standards. The operators become specialists. Practice on various materials. Steel compositions. Different thicknesses. Understand how materials respond to thermal cutting. Recognize when tool is appropriate. When other methods better suited. The decision matrix. Situation dependent. Time available. Material type. Environmental conditions. Operator expertise. Mission parameters. All factor into tool selection. Require State Department approval for foreign sales. Even to allies. The controls aim to prevent hostile acquisition. Technology theft. Reverse engineering. Keep advanced breaching capabilities restricted. But information leaks. Technical details appear online. Specifications. Performance data. Other nations develop indigenous capabilities. China, Russia, domestic thermite torch programs may lack MPI's refinement, but demonstrate concept viability. The proliferation challenge, preventing terrorist groups from acquiring technology, non-state actors, insurgent forces. The devices would provide significant advantage, breaching hardened positions, attacking protected targets, security measures around tech torch deployment, controlled storage, operator accountability, post-mission equipment checks, prevent theft or loss, the few units that go missing, immediate investigations, recovery operations, the risk of improvised variants, criminals attempting to build similar devices using publicly available information. The engineering challenge is significant, but not insurmountable. Law enforcement monitors thermite purchases, precursor chemicals, aluminum powder, iron oxide, suspicious buying patterns, quantity thresholds, regulatory oversight. Universities study thermite reactions, combustion dynamics, heat transfer mechanisms, metallurgical effects, papers published, peer-reviewed journals. The research typically focuses on traditional thermite, not military applications. The academic interest, materials science, pyrotechnics, chemical engineering. The fundamental questions, reaction kinetics. How fast does thermite burn under different conditions, pressure effects? Confinement increases reaction rate, additives. How do different metals affect performance? Copper thermite, manganese thermite. Each has characteristics. The computational modeling, simulating thermite reactions, finite element analysis, predicting temperatures, burn times, optimization studies, maximize energy output, minimize unwanted byproducts, the experimental work, laboratory scale tests. High-speed cameras capture reaction progression. Thermocouples measure temperature profiles. Spectroscopy analyzes combustion products. The safety research, understanding ignition sensitivity. How easily can thermite be accidentally ignited? Friction sensitivity, impact sensitivity, electrostatic discharge. The data informs safe handling procedures, manufacturing protocols, storage requirements, the environmental studies, combustion products, aluminum oxide particles, iron dust, airborne contaminants, occupational health concerns, long-term exposure effects. The research accumulates, knowledge base expands, future developments benefit from scientific understanding, better formulations, improved performance, enhanced safety, the academic-military connection. SBIR programs fund university research, technology transfer mechanisms, graduate students work on defense-relevant problems, publications limited by classification. But basic science remains open, the balance between advancing knowledge and protecting capability, the public fascination with extreme heat, temperatures that melt steel, devices that cut through barriers instantly. The videos go viral, YouTube demonstrations, cutting locks, penetrating plates. The view counts reach millions. Comment sections fill with speculation. Could this cut through bank vaults? Could criminals use this? Could you build one yourself? The responsible outlets emphasize professional use only. Military and law enforcement applications. But information spreads regardless. The detailed specifications available, burn temperature, cutting times, material capacities, the engineering explanations, how thermite works, why it cuts so effectively. The balance between public information and operational security. Too much detail aids adversaries. Too little generates misinformation and myths. The news cycle moves on. Later articles mention TC torch in passing. Included in lists of special operations equipment, military technology roundups. The device becomes part of the toolkit, no longer novelty, established capability. The ongoing development remains largely unpublicized. Military preference. Avoid telegraphing capabilities. Keep adversaries uncertain about friendly force equipment. The element of surprise matters tactically. The commercial derivatives possible. Once core patents expire, other manufacturers could enter market. Competition drives prices down, capabilities improve, but the regulatory barriers remain. Thermite devices classified as destructive devices in many jurisdictions. Licensing requirements, background checks, fees, limits market size, prevents mass adoption. The alternative uses proposed, hobbyist metalworking, artistic applications, thermite cutting for sculptures, but risks too high, untrained operators, inadequate safety measures, fire hazards, injury potential, the liability exposure for manufacturers, product misuse, negligence claims, legal costs. Most companies avoid consumer thermite products, stick to industrial and professional markets, established customers, training programs, contractual protections. The few consumer thermite products available. Small quantities for demonstrations, educational purposes, science experiments, heavily regulated, warning labels, usage restrictions, the contrast with military-grade devices. Techie torch represents cutting edge. Consumer products pale in comparison. Performance gap intentional. Professional tools for professional users. Law enforcement tactical teams. First responders. The technology proven, combat tested. Reliable performance. The units accumulate operational hours. Hundreds of uses. Thousands of cuts. The maintenance data positive. Low failure rates. Predictable wear patterns. Cartridge storage life acceptable. No degradation over typical storage periods. The user feedback positive. Operators report confidence in the tool. Know it will function when needed. The mission reports document successes. Breaches completed within timeline. Lives saved through rapid extraction. Equipment destroyed to prevent capture. The thermite torch contribution measurable, but classified details remain restricted. Specific operations, tactics, enemy responses. The general capability acknowledged publicly. Handheld thermal cutting device. Uses thermite reaction. Cuts hardened steel in seconds. The specifics protected. Exact formulations. Nozzle geometries. Performance parameters against classified target sets. The balance between transparency and security. Public has right to know how tax dollars spent. Military has need to protect operational capabilities. The compromise: general information released, technical details restricted. Enough for informed debate, not enough for adversary exploitation. Smaller cartridges, reduced weight, enhanced portability, the performance improvements, faster cutting times, thicker material penetration, extended burn duration, the new applications, infrastructure protection, critical facility security, cutting through vehicle barriers during emergencies, the underwater uses expanding, submarine rescue, salvage operations, offshore energy installations, the space applications, theoretical, zero gravity, thermite cutting, orbital debris removal, spacecraft disassembly, challenges remain, oxygen supply in vacuum, containment without atmospheric pressure, thermal management in vacuum, research proposals submitted, initial studies conducted, decades before practical deployment, but thermite's self-contained oxygen makes it candidate technology. The Mars applications, surface operations, cutting through rock formations, ice deposits, equipment repairs. Thermite works in thin atmosphere, Martian surface pressure, 1% of Earth, insufficient for conventional combustion, but thermite supplies own oxygen. Reaction proceeds normally. The speculation outpaces reality, but engineers consider possibilities. Future missions may include thermite tools, cutting, welding, heat source. The versatility appeals to mission planners. One technology, multiple applications. Reduced equipment mass, space mission critical parameter. Molecular dynamics simulations, quantum mechanical calculations, predicting reaction pathways at atomic level. The experimental techniques advance, laser diagnostics, in situ measurements, real-time analysis of burning thermite, temperature distributions, species concentrations, reaction zone structure. The knowledge gained feeds back into applications. Better formulations emerge, tailored properties for specific uses. Fast burning thermite for shaped charges, slow burning for sustained heating, high temperature variants, moderate temperature alternatives. The materials science angle, thermite as synthesis route, producing advanced materials, nanoparticles, alloys, composite structures. The rapid heating and cooling creates unique microstructures, properties unattainable through conventional processing. The patents filed on these methods, commercial potential, industrial processes, manufacturing techniques, the thermite research community, international conferences, technical symposia, researchers from multiple nations, academic institutions, government laboratories, defense contractors, share findings, collaborate on problems, advance the field collectively, the dual-use nature. Same research benefits military applications and civilian technologies. The funding sources reflect this. Defense budgets, industrial partnerships, academic grants. The progress continues. Increasingly safe operations, residual risk accepted. No technology eliminates risk entirely, but thermite tools achieve acceptable safety levels, comparable to other dangerous equipment. Explosive breaching charges, plasma cutters, oxy-fuel torches. Professional users manage risks through training and procedures. The regulatory framework evolves, new standards developed, testing protocols, certification requirements, inspection schedules. The industry self-regulates partially, best practices shared. Professional associations form, equipment manufacturers cooperate on safety standards. Customer demands drive improvements, military procurement specifications, law enforcement requirements, insurance company conditions. The market pressures reinforce technical improvements, safer designs, more reliable components, better training materials. The liability environment incentivizes care. Manufacturers face lawsuits from accidents, settle claims, improve products to prevent recurrence. The legal system is feedback mechanism, pushing technology toward greater safety, the balance imperfect, but functional. Deaths and injuries minimized, capability maintained. Construction, thermite parallels, Goldschmidt, 1893, controlled aluminothermic reaction, changed welding, metalworking, military applications, both technologies, simple chemistry, profound impacts. The thermite reaction, less famous than explosives, but equally significant in its domain. The cutting and welding applications, infrastructure dependent on them, railroads, pipelines, buildings, ships. The military uses less visible, but strategically important. The thermite torch, latest evolution. Handheld variant of century-old chemistry, modern engineering applied to classical reaction. The pattern repeats throughout history. Fundamental discoveries, long development periods, eventually miniaturized and refined, become practical tools. The steam engine, centuries from concept to industrial revolution. The internal combustion engine, decades of development. The transistor, years before integrated circuits. The thermite torch, 120 years. From discovery to handheld deployment, the timescales vary, but the pattern holds. Innovation requires both discovery and development. The scientific breakthrough enables. The engineering effort realizes, both necessary, neither sufficient alone. Ignites the mixture. Witnesses 2,500 degree reaction. Takes notes. Files patent. 1899. Essen Tramway, first thermite weld, continuous rail. 1922, Leo Melcher, thermal lance patent, oxygen-fed metal tube, burns through steel. 1940s, World War II, thermite incendiary bombs, cities burn. 2013, EMPI, tech torch, handheld thermite cutter, 2-second steel penetration. One technology, multiple forms, constant evolution. The chemistry unchanged. Aluminum still reduces iron oxide. Temperature still 2,500 Celsius. But applications transformed. From laboratory reaction to industrial process to portable tool, each generation builds on previous. Each application enables next. The art continues. Future developments await. But the foundation's solid. Goldschmidt's discovery. Simple mixture. Profound implications. Cuts through what's supposed to be impenetrable. Not through high-tech wizardry. Through basic chemistry, rust, and aluminum. Two of the most common elements, combined correctly, ignited properly, release temperatures that melt steel. The primitive torch, cutting through modern barriers. The paradox appeals. Low-tech solution to high-security problems. No computers, no exotic materials, just exothermic oxidation reduction. The oldest type of chemical reaction. Harnessed, directed, deployed. Both have limitations. The thermite torch exploits the melting capability. Focused application. Precise energy delivery. 2 seconds of controlled 4,000 degree heat. Exactly where needed. The engineering achievement, taking that raw reaction, packaging it safely, making it portable, giving it to operators, who carry it into dangerous situations, trust their lives to it. The reliability requirement absolute, must function every time. Lives depend on it. Missions succeed or fail based on whether the breach works, the pressure on manufacturers, the responsibility, the quality control, the testing regimens, everything to ensure that when an operator squeezes that trigger, the cartridge ignites, the thermite burns, the metal vapor jet cuts through the target, and the mission continues. That reliability, built on Goldschmidt's discovery, refined through a century of applications, miniaturized through modern engineering, deployed through military logistics, proven in combat and rescue scenarios worldwide, hitting the fire button. 2-second burn. The rod separates cleanly. Cut surfaces measured, within specifications. Batch approved for shipment. The cartridges packaged carefully. Shipped to military supply depots. Distributed to units. Operators load them into packs. Deploy to operations. When needed, an operator pulls the handle from a pouch. Loads a cartridge. Aims at a lock securing a gate. Activates. 2 seconds later, the lock falls away. Gate swings open. Team moves through. Mission continues. Somewhere in that chain, from quality control tech to forward operator, Goldschmidt's chemistry does what it has done for 132 years. Aluminum reduces iron oxide, produces heat and molten metal, but now in a form that fits in a cargo pocket and cuts through hardened steel in the time it takes to blink twice. That's the primitive torch that cuts through impenetrable steel. Not primitive at all, just pure, refined, weaponized chemistry.